Okay, so let's consider an example of a system that's in equilibrium. So in this example, we have a loaded Apache helicopter that's moving horizontally to the right at a constant velocity. The mass of the helicopter is 8,000 kilograms, and there's a lift force that's generated by the rotating blades that makes an angle of 35 degrees with respect to the horizontal. What is the magnitude of the lift force? And we also want to determine the magnitude of the air resistance that opposes the motion. So the first thing that we would see when we read through this problem is that the helicopter is moving with a constant velocity to the right. And so the fact that it's moving with a constant velocity tells us that this system has zero acceleration. And according to Newton's laws of motion, that means that the system is essentially in equilibrium. So that means that the sum of the forces that are acting on the object have to be equal to zero. Now we can separate this vector expression for Newton's second law into the fact that the sum of the forces along one dimension, say the x direction, have to be zero, and the sum of the forces along the y direction have to be equal to zero. So before we can try to work out this problem, the first thing that we should do is to go ahead and draw in all the forces that are acting on our system, and also to identify a coordinate system. So in our picture, we already have a resistive force that's acting back and a lift force that's acting up. They do tell us in the problem that that lift force makes an angle of 35 degrees with respect to the horizontal. So this angle here is 35 degrees. And then we also know the fact that this helicopter has a mass of 8,000 kilograms. So we know that the force of gravity is acting on the helicopter, which is just its mass times the gravitational acceleration. So this is just going to be 8,000 kilograms times 9.8 meters per second squared. And so that gives us a force of gravity of 78,400 newtons. All right, so we have all the forces that are acting on our system. The next thing that we're going to want to do is we're going to want to choose a coordinate system. So it makes sense to choose a coordinate system in the direction that the helicopter is moving, which is horizontally, and then to choose another axis of our coordinate system to be perpendicular to that. All right, so we've identified the fact that the system is in equilibrium. We've written down all the forces that are acting on our object. And so the next step would be to draw a free body diagram with all of the forces acting on that object such that they are resolved into components. And when we do that, we make sure that we just draw our object as a dot. So two of the forces are already in our traditional coordinate system, to the right and then vertically. And so we can draw those forces in. So we've got this resistive force, which is acting to the left, and we have this force of gravity, which is acting down. Now, on the other hand, we also have this lift force, and that lift force makes an angle in our coordinate system. So we need to resolve that lift force into a component that is horizontal and a component which is vertical. And we'll call the horizontal component the x component of the lift, and then we will call the vertical component the y component of the lift. We have a right triangle here, and we know, according to our right triangle, that we have the trig identities that we can use, or the trig functions. The hypotenuse of our triangle is the actual lift force itself, and so we can write down that the lift force in the x direction, or maybe we should do it this way, that cosine of 35 degrees is equal to the adjacent side of the triangle, which is the x component of the lift, over the hypotenuse, which is the magnitude of the lift. And so we can write down the x component of the lift as being the magnitude times cosine of 35 degrees. And then we can do the same thing using the sine function. Sine is the opposite side of the triangle, which is the y component of the lift, over the magnitude of the lift. And so the y component is just the magnitude of the lift times sine of 35 degrees. So we can now add those two components of our lift into our free body diagram. And so we had a component in the x direction, which was L times cosine of 35, and we had a component in the y direction, which was L times sine of 35 degrees. So once we have our free body diagram, we don't have to look at our original picture. We can simply look at our free body diagram picture, and we can look at the forces that are acting, and hopefully we can solve for any unknown forces. So we can use the fact that the sum of the forces that are acting along the x direction have to be equal to 0, and the sum of the forces acting along the y direction also have to be equal to 0. So in my x direction, I have this component of the lift force that is the cosine component of the lift, and that's acting in the positive x direction. And then acting in the negative x direction, I have this resistive force, R. So I can move the resistive force to the other side of the equation, and I get that the amount of resistance is just dependent on what the lift force is and cosine of that angle. Now I don't know what the lift is at this point, so I'm at a stopping point, and I need to look at what the forces are in the y direction and see if that helps me. So when I look at my free body diagram again, I have this upward lift force in the y direction, which is L times sine of 35 degrees. And then acting down, I have the force of gravity, so that's negative. And those have to add up to 0 because the system is in equilibrium. So I can move the force of gravity to the other side of the equation. And now I have an equation that only involves this upward lift force that I'm interested in. So I can divide both sides by sine of 35, and I will be able to determine what that lift force is. And so when I divide that, I get 136,686 newtons. We probably don't need to keep that many sig figs, but I'll go ahead and just leave that in there. Once I know what this lift force is, which is one of the values that we wanted to find, I can use that expression and I can plug it back in over here for my lift force. So my lift is the value that I found, and if I multiply that by cosine of 35 degrees, that's going to give me the resistive force. And so when I do that, I get 111,966 newtons. So now I have my resistive force as well. So that's an example of a system that's in equilibrium, but the steps that we will follow to solve those types of problems are all the same steps. So we'll identify the forces, draw them in our picture, resolve forces into components after we choose a coordinate system, draw the free body diagram, and then apply Newton's second law.